The Shannon number. If you tried to play out every possible game of chess, one after another, you would run out of universe before you ran out of games. In 1950, mathematician Claude Shannon tried to estimate how many distinct games of chess could ever be played, and the number he landed on broke intuition immediately. It's not about how complex any single game feels while you're playing it. It's about the sheer branching of possibility. Every legal move opening a new fork. Every fork opening dozens more. Shannon estimated the total game tree complexity of chess at around 10 to the 120th power, a number so large it dwarfs the roughly 10 to the 80th power atoms thought to exist in the observable universe. If every atom in the universe were itself a separate universe, and every atom inside those universes played one game of chess, you still would not reach the Shannon number. And chess is only 8 by 8 squares with 6 types of pieces. The Skewes number. For a long time, mathematicians believed a simple pattern about prime numbers would hold forever. The function counting how many primes exist below a number was always thought to fall short of a related estimate called the logarithmic integral. No exceptions, no crossover. In 1933, Stanley Skewes proved that pattern eventually breaks. That's somewhere. The primes overtake the estimate. The unsettling part is where. Skewes calculated an upper bound for this crossover, and the number he produced was so large it needed to be written as a tower of exponents just to fit on a page. Roughly 10 raised to the 10th power, raised again to the 10th power, raised again into the 30s. The Googolplex. A Googolplex cannot be written down, not because no one has tried, but because there isn't enough matter in the universe to do it. A googol is 1 followed by 100 zeros, already larger than the number of atoms in the observable universe. A Googolplex is 1 followed by a googol zeros, meaning if you tried to print every digit, 1 atom of ink per digit, you would need more atoms than exist in reality to finish the number, let alone read it. The concept is simple enough for a child to grasp, a 1 and a lot of zeros, yet it produces a number that physically cannot be represented by the universe that contains the person thinking about it. Mathematicians can manipulate the Googolplex perfectly well in equations. It behaves like any other number, obeys the same rules of arithmetic, sits neatly on the number line. It simply cannot be written in decimal form by any physical process anyone will ever perform. It exists entirely as an idea that outgrew the universe meant to hold it. Kaprekar's constant. Take any 4-digit number, as long as its digits aren't all identical. Arrange its digits from largest to smallest, then smallest to largest, and subtract the second from the first. Do it again with the result. And again. Every single time, no matter what number you started with, you will land on exactly 6174 within 7 steps at most. And once you hit it, you're trapped there forever, because repeating the process on 6174 just produces 6174 again. Discovered by Indian mathematician Dr. Kaprekar in 1949, this number behaves like a drain that every 4-digit number eventually gets pulled into. The Rubik's Cube state space. A Rubik's Cube looks like a toy you could exhaust in an afternoon. It hides 43,252,074,489,856,000 possible configurations, more than 43 quintillion. If every person on Earth had been given 1 billion Rubik's Cubes each, and every single one were in a different arrangement, you still would not come close to covering every possible state. For decades, no one knew the minimum number of moves needed to solve any cube from any starting position. In 2010, a team using Google's spare computing power finally proved the answer. 20 moves, no matter how scrambled the cube is, it can always be solved in 20 moves or fewer. That number, now called God's number, took roughly 35 CPU years of computation to confirm, sorting the entire 43 quintillion state space into groups and proving every group solvable within that limit. A plastic puzzle sold in toy stores turned out to require one of the larger brute force computer proofs in mathematical history just to fully understand. The busy Beaver numbers. Some numbers aren't just large, they are mathematically forbidden from ever being fully known. The busy Beaver function asks a simple question. Given a computer with a certain number of instructions, what is the longest it can possibly run before it stops? For small machines, the answer is knowable. A 5-instruction machine, mathematicians proved in 2024, after decades of effort, runs for exactly 47,176,870 steps at most before halting. But the function grows faster than any formula, faster than exponentials, faster than towers of exponents, because computing it exactly for larger machines is provably impossible. Alan Turing's own work on computability shows that no algorithm can ever determine, in general, whether a given program halts at all. That means the 6-instruction busy Beaver number is not just unknown, it may be permanently unknowable through ordinary mathematics, hiding behind machines whose behavior resembles unsolved conjectures in number theory. Somewhere past 5 instructions, the universe of computable numbers ends, and mathematicians are left proving that certain numbers exist without ever being able to calculate what they are. Graham's number was, for a time, listed in the Guinness Book of World Records as the largest number ever used in a serious mathematical proof. It emerged from a problem in Ramsey theory involving connecting the corners of a multidimensional cube with colored lines, and the answer turned out to be too large for ordinary exponents to express. Mathematicians had to invent an entirely new notation, Knuth's up arrow notation, stacking towers of exponents on top of towers of exponents, just to define it. If you tried to store every digit of Graham's number using the Planck length, the smallest unit of space physics allows, Rayo's number. In 2007, at a debate between MIT graduate students nicknamed the Big Number Duel, a philosopher named Agustin Rayo defined a number engineered to be the largest ever named in a legitimate mathematical framework. Rayo's number is defined as the smallest number larger than any number that can be uniquely described using a Googol symbols or fewer, written in the formal language of first-order set theory. The definition is self-referential in a way that outmaneuvers every other big number construction, Graham's number, tree-based functions, tower after tower of up arrows, because all of those can themselves be described within a Googol symbols, and are therefore, by definition, smaller than Rayo's number. It doesn't just beat other giant numbers, it's constructed to guarantee it beats every giant number anyone could ever define using that much language. The unsettling part isn't the size, it's that Rayo's number reveals a kind of number too large to be pinned down by ordinary construction, only by a rule about language itself, a number defined not by what it is, but by everything it is guaranteed to exceed. Chaitin's constant. Somewhere between 0 and 1 sits a real number that mathematics proves exists, and proves can never be fully known. Chaitin's constant, usually written as omega, represents the probability that a randomly constructed computer program will eventually halt rather than run forever. It is a perfectly well-defined number. Mathematicians can prove it has an exact value. But Gregory Chaitin proves something stranger alongside it. The digits of omega are algorithmically random, meaning no computer program shorter than the digits themselves can ever calculate them. Knowing even a few hundred digits of Chaitin's constant would let you solve an enormous range of the most famous unsolved problems in mathematics. Tree of 3. Graham's number, once considered the benchmark for incomprehensible size, is not just beaten by Tree of 3, it isn't even close. Tree of 3 comes from a gentler sounding question in graph theory about how many different trees you can build out of colored seeds before you're forced to repeat a pattern, a rule known as Kruskal's tree theorem. The function starts off almost insultingly small. Tree of 1 equals 1. Tree of 2 equals 3. It looks like nothing is going to happen. Then tree of 3 explodes into a number so large that Graham's number, the number of numbers no one will ever name. This is the most disturbing number of all, and it isn't really a single number, it's a proof about all of them. Every number that has ever been written, spoken, or programmed into a computer had to be described using some finite string of symbols, a decimal expansion, a formula, a name like Graham's number or tree. There are only countably many finite strings of symbols that will ever be written across all of human history, no matter how long civilization lasts. But the real numbers, the full, continuous number line, are provably uncountable, a strictly larger kind of infinity, first proven by Georg Cantor in the 1870s. The conclusion is unavoidable. The vast, overwhelming majority of numbers that exist between 0 and 1 will never be described by any sentence, symbol, or computer program, ever, by anyone.